The laws of thermodynamics. There are two laws of thermodynamics. The first law being the change in internal energy is equal to the heat transferred to a system plus the work done. So again, delta U is the change in internal energy of a closed system. Q is the heat transferred to the system. And lastly, W is the work done on or by a system. All of these terms, change in internal energy, heat, and work, they are all in the unit of the joule, the SI unit for energy. There is also a formula for work. And we know work is equal to a parallel force multiplied by its displacement. If we're in a closed system, it's also equal to a negative constant pressure within that system multiplied by a change in volume of that system. So if you have no change in volume of that system, like for example, you have a rigid container, then we can say no work has been done. But if you have a system where the volume is allowed to change, then we can calculate the work that was done based on that change in volume. Now let's say we have some sort of glass flask or some sort of flask, and we put some water inside, and then on top of the opening of the flask, we put a balloon. In this case, I put a purple balloon. And then what we do is we put this flask with the water in it over a flame so that heat starts going into the system. As heat starts going into the system, the balloon on the flask will start to expand. As the water molecules convert to liquid water to water vapor, we get a situation that looks like this. So heat has gone into the system, and some of the liquid water is turned into gaseous water. The pressure of the system inside has increased, so the balloon will then start to expand. And we say in this situation that we have a increase in volume. The volume has increased, or we have a positive delta V. And we have a positive delta V because this steam inside the system is pushing on the balloon, which then the balloon expands. So we say work is done by the gas inside this container, or we say work has been done by the system. And this is because we have an increase in volume. Now the reverse is true, where let's say now we take this system, the flask with the water and the balloon, and we remove it from the heat. Eventually heat will start to leave the system, and the size of the balloon will decrease. It'll probably go back to what it originally looked like, something like this. So in this case, now heat has left the system, the volume of the balloon has decreased, or we say we have a negative delta V. The outside pressure is more than the inside, so we say that work is being done on the gas that's inside the system, or work is being done on the system. So whether or not work has been done by the system or on the system depends on what's happening with the volume. So let me just repeat this. If the volume increases, or a plus delta V, then we say work is being done by the system. If the volume decreases, or we have a negative delta V, then we say work is being done on the system. I have a little chart here to show what a positive value or a negative value will indicate. So if we have a positive delta U, or a positive change in internal energy, we say the internal energy has increased. If we have a negative delta U, the internal energy has decreased. If we have a positive Q, heat has been added to the system. If we have a negative Q, heat has been removed to the system. If we have a positive work value, work has been done on the system, and if we have a negative W, work has been done by the system. Again, just to repeat, if work has been done on the system, or plus W, we say that the volume has decreased. If work is being done by the system, or negative W, volume has increased. Let's do a quick little example. Let's say we have heat going into a system, being added to a system of 2,500 joules. We have work being done on a system of 1,800 joules. So that's plus because the work is being done on. And the question is, what is the change in internal energy? The first law of thermodynamics says the change in internal energy is equal to Q plus W. So my delta U will be a positive 2,500 joules plus a positive 1,800 joules. And so my delta U is a value of 4,300 joules. All right, so now let's talk about thermodynamic processes. In each of these different types of thermodynamic processes, there will be a fixed mass, so fixed number of moles, in a closed container with a movable piston. And when I say we have a movable piston, what that means is that the volume is allowed to change. It is not a rigid container. The first type of thermodynamic process is called an isothermal process. And iso meaning same and thermal meaning temperature. So we have some sort of process where the temperature is constant, and this is typically talked about in terms of PV diagrams, or pressure versus volume graphs. So if we had a pressure versus volume graph, or a PV diagram of an isothermal process, it would look something like this. We would have some sort of curve, and the work done in this case, if we were interested in finding the work done would be the area under this curve. So if I could find this area under this curve, I could find the work done in this process. Now keep in mind, temperature is constant, so a change in temperature would be equal to 0. Temperature is directly proportional to internal energy. So if my change in temperature is 0, my change in internal energy is 0. And using the first law of thermodynamics, then, my heat transferred is equal to the negative work done in an isothermal process. Now, the next thermodynamic process is referred to as an adiabatic process. In this case, instead of the temperature being the same, there's no heat transfer, or in other words, Q is equal to 0. This would happen if you had some sort of excellent insulation, or some sort of very, very quick process or rapid process where the volume expanded or contracted in a very, very short amount of time. A PV diagram in this case is very similar looking to an isothermal diagram. The curve is just a little bit lower, closer to the x-axis when we have a Q equaling 0. But again, we could find the work done by finding the area under this curve. We know that Q is equal to 0, and again, the first law of thermodynamics being delta U is Q plus W. With Q being 0, we can see that the change in internal energy is also equal to the work done. Going back above the... The third thermodynamic process is called an isobaric process, which means constant pressure. PV diagram here shows some sort of horizontal line. So let's see, between steps A and B, we have a constant pressure. The work done in this case is still the area under that line, or we can say the work is equal to the negative constant pressure value multiplied by the change in volume between points A and B. If we're interested in looking at the first law of thermodynamics, which is the change in internal energy is equal to Q plus W, we can plug in for work our negative pressure times change in volume for W. The last process is an isovolumetric process, or sometimes called an isochoric process, and that is referring to a constant volume. So if we have a PV diagram showing constant volume, we have a vertical line from, say, points A to B. In this case, hopefully you can see that there is no change in volume. There's a change in pressure, but no change in volume. The volume's constant. And because there's no change in volume, then the work is equal to 0. Using the first law of thermodynamics, we can see then that delta U is equal to Q. So how can we apply a PV diagram showing more than one thermodynamic process? This will occur in a cyclic process. An example of something that uses more than one thermodynamic process would be a heat engine. So we're going to have a PV diagram, and we have a case where maybe we have an isothermal process from, say, point A to point B. From point B to, say, point D, we have an isobaric process, and from point A to D, we have an isovolumetric process. Now, to find the work done in this case, it's actually going to be the area of the encased shape, and that would be the work done in this case. When the pressure is constant, if we see that there is an increase in volume, we will say that there is work done by the system. Okay, let's do an example. So we have some sort of fixed mass of 0.25 moles. We have an initial temperature of 1,150 Kelvin. It goes to a final temperature of 400 Kelvin, so we've lost some heat. Or something else has changed. Why don't we go ahead and say that we haven't lost any heat? Let's say we have an adiabatic situation, because it was a rapid situation, so that we have a Q value of 0. And using the first law of thermodynamics, then we know that my change in internal energy is going to be equal to the work done. And why don't we go ahead and determine what is that work done? Well, if we could find the change in internal energy, we will know the work done. And so let's see if we could find that change in internal energy. Change in anything is going to be a final amount minus an initial amount. And from a previous chapter, we see that there's a relationship between internal energy and temperature, and that relationship is shown here, that final internal energy minus initial internal energy is equal to 3/2 nR multiplied by T final minus T initial. So my delta U then will be 3/2 multiplied by 0.25 moles multiplied by the constant 8.314 joules per mole per Kelvin multiplied by a change in temperature of 400 Kelvin minus 1150 Kelvin. And I get an answer of negative 2300 joules is my change in internal energy. That's also equal to my work done. We can also see that the work is done by the system because we have a negative value for work. Okay, now let's talk about the second law of thermodynamics. Basically, the second law of thermodynamics says that heat naturally flows from a higher temperature to a lower temperature. Sometimes written as, if we have a T sub H on one side, we have a T sub L on the other side, we will have heat will flow in one direction from the higher temperature to the lower temperature. And because this happens, we can use this idea to then investigate heat engines, and that's what I'd like to talk about next. Now, there's a very general model of a heat engine, and it looks something like this. At the top here we have some sort of a high temperature, At the bottom we have a lower temperature. So the most important thing we need for a heat engine is a difference in temperature. Because if we have a difference in temperature, we know heat will flow. And heat at the higher temperature will flow down to the lower temperature side. The way a heat engine works is we have some sort of gas or medium that the heat flows through. And when the heat flows through the medium will then expand. And what heat engines do is they have some sort of side arm. If we're talking about a car engine, this would be a piston. And it's allowed to move back and forth. And when this gas expands from heat flowing through it, it actually pushes on this piston, and the piston will actually move some displacement to the right. And when the piston moves to the right, we say work has been done by the system, by increasing the volume. And so there's a formula that has been written for heat engines that says the total heat at the high end is equal to the work that is done by moving the piston from the expanding gas, plus any heat that goes out at the lower temperature. Typically, if we're talking about a car engine, this is the heat that leaves through the exhaust. So when we start talking about heat engines and work done, we want to know how efficient is it? How much heat is lost through the exhaust? If it was 100% efficient, all of the heat by the high temperature would be used to do work. But of course we lose a lot through the exhaust. So the question is, how efficient is it? And there's a formula for that. Your efficiency is equal to the work done by that piston moving divided by how much heat that goes into the engine. And of course from the above equation we also know QH is equal to W plus QL. Or we could say W is equal to, the work done is equal to the heat at the high temperature plus the heat at the lower temperature. We can then plug this in for work, so my efficiency is equal to the heat at the high plus the heat at the low over heat at the high. We can also write that as 1 plus QL over QH. And so these are the formulas we can use for the efficiency of any real engine. A scientist by the name of Carnot, French scientist Carnot, came up with a more theoretical type of engine, or referred to as an ideal engine, where there aren't certain things like turbulence or friction. And he came up with a formula we call the E-ideal, efficiency of an ideal engine, which doesn't exist, but we can look at, we can compare what a real engine does compared to the ideal to determine, how much friction is involved. And that's equal to not the heat at the high temperature, but the actual temperature. So the high temperature minus the low temperature over the high temperature, or 1 minus TL over TH. And these temperatures, of course, are in Kelvin. The last thing I want to talk to you about is another way of referring to the second law of thermodynamics, and that's through a term called entropy. Entropy is simply a measurement of disorder of a system. The second law of thermodynamics says, during a natural process, as time passes, S increases. Or we can say, as time passes, the disorder of a system increases. Examples of situations where you have high order is when you have situations where you have high separation of different variables within a system. Let me give you a couple examples. Now, if you have a situation where you have a separation in temperature, we consider that to be a high-ordered system. But as time goes on, thermal equilibrium will be reached. Thermal equilibrium means the temperature is the same everywhere, so this would indicate high disorder or high S value. A separate egg yolk and an egg white indicates a separation, so that would be high order or low S value. And as time goes on, say through just normal vibrations or maybe even through some mixing, we then get the scrambling of the egg or a mixture, and that would represent high disorder. So scrambled eggs. My last example is, say you have a clean bedroom where everything is in its place, and as time goes on, things get mixed in together, and then now you have a messy bedroom, high disorder. Alrighty, here's your practice. Good luck. See you when we come back from vacation.